speaker. Anna, could you introduce?
Yeah, François Mercier-Tigrine is co-founder and scientific director of HD Rain. The company specializes in combining AI with meteorological measurements and expertise to provide highly accurate weather information forecasts and data certification based in particular on satellite microwave link opportunistic rainfall measurements. The company collaborates with various sectors such as insurance, local authorities, or governmental agencies. François is within the OpenSense Action a member of Working Group 1. And with this said, François, if you are ready, you are. The floor is yours.
Yes, thank you very much, Anna. Thank you, everyone. So yes, this presentation will be very complementary, I guess, with Filippo's presentation. So indeed, I will present some results that we get at HD Rain together with the LATMOS laboratory near Paris in France. So HD Rain is indeed a company which provides weather measurements and expertise. So we analyze SML data, but we also produce a more value-added product like alerts for rain, but also for temperature, air moisture, etc., to insurances and cities mainly, or public sector. So I will introduce in the first time the technology we use. So it's the same as the one introduced by Filippo. And in the second part, I will focus on a few issues that we have and we try to improve our measurements. So this is the sensor that we use. So it's a commercial dish targeting a geosynchronous satellite. It's powered with a solar panel, and so we build a box that is able to measure the power of the signal coming from the geosynchronous satellite. So here it's a standard LNB. Cheaper in LNB, and we transmit the data recorded by the system to a central server using GSM, so 2G or 4G with an antenna. So we work in the Ku band, so around 12 gigahertz, and this sensor do sequentially 4 different measurements over 4 different channels, depending on the frequency used and on the polarization. And so for each sensor, we get 4 different time series. So there is one measurement, which is the average power received on the lower part of the Ku band, around 11 gigahertz. Another one on the upper part of the Ku band, and both are decline in horizontal or vertical polarization. So this is an example of the signal we can receive. So it's very classical. You can see the rain event here. So it was in the south of France. And in this case, we use the satellite, which emits a strong signal for both frequencies and polarization. So this is the same behavior for all 4 channels, with a decrease of the signal due to the attenuation produced by the raindrops on the signal. We will see in the second part that it's not always the case, especially when we target satellites which emits very weak or no signal for 1 or 2 of these channels. So this is a summary of the operational treatments that we produce to this data, because our goal is to produce in real time rain maps and short-term prediction, no casting. So we have sensors on the ground that transmit the data in real time using GSM to a server. So here we centralize the raw signals measured by all the sensors. Then, Filippo explained this before, we need to get the baseline, which is the level of the signal that we would get if it was not raining. So to do this, we use a machine learning algorithm. So it's based on LSTM. So this machine learning algorithm for now doesn't draw directly the baseline, but just a classification algorithm. So for each time sample, it decides if it's raining or not raining, and then we draw the baseline, considering the time when it starts raining and when it stops raining, if the event is finished. So we draw a constant baseline during the rain event, and we adjust the baseline after the rain event. So once we have the baseline, we can calculate the attenuation due to rain, the difference between the baseline and the effective signal that is measured. And then we use AR standard relationships to translate this into rain rates. So as Filippo said, to do this, we need to know the length of the path in the liquid phase of the rain event. We need the freezing level, and especially in France, we need a dynamical freezing level because it ranges from 0 in winter to 4 kilometers in midsummer. And so in real time, we get the freezing level from the global numerical weather prediction model from Météo France, ARPEJ. Why ARPEJ? Because it's available all over the world, so we can use the same code to work everywhere. So we call the model every 6 hours to get a refreshed dynamical freezing level, and it allows us to estimate the rain rates for each sensor, and then we merge the rain rates from all the network of sensors into a data assimilation algorithm. So basically, we suppose that during a time window, like 20 or 30 minutes, the rain fields are moved according to the wind in high altitude. So we have a model to link the measurements that are recorded at different places at different time, and using data assimilation, we get the rain field that is the most stable to explain all the measurements that we have recording during this time window. So it's a minimization process, and we repeat this process every 5 minutes to update the rain field that is deduced. And for the nowcasting, up to now, it's very simple and basic. We just apply again this two-dimensional wind field to advect, to transport the rain fields for the next 30 minutes or 60 minutes. And so the wind field in high altitude is also deduced from ARPEJ, the global model of Météo France. So this is a technique introduced by Zinevich like 10 or 15 years ago, and that we use since then. We are working right now to try to use machine learning as well to do the spatialization part. It's a work in progress, not finished, but it's quite promising. So this is our operational way of treating this data. And so just a slide to show where we have sensors. So basically in 2 places, most of them are in 2 places, in the south of France and in Ivory Coast. So in the south of France, we installed our stations through a partnership with the fire station. So it's an area subject to flash floods, and so we're in an interest to have a dense network of rain monitoring. And in Ivory Coast, it's through a partnership with the National Weather Service of Ivory Coast in Abidjan. And so we installed a set of sensors here in the metropolitan area of Abidjan, but also in this area eastward of Abidjan, because most of the strong rain events here comes from the east, and so we needed sensor here to be able to do a nowcasting in Abidjan in case of strong rainfall events arriving. So this is just a slide to show you how we deliver the information. So we have a web application to show the rainfall in real time, the daily accumulations, for instance, or the measurements for one specific station. So I just have a few slides about very global overall results. So the main conclusion is that at a large scale, there are no overall biases. It works quite well. But then I will show that there are, of course, discrepancies at small scales, and we will try to explain these discrepancies and to see how we can correct them. So this is a map showing the rain accumulation for a few months in the south of France. So the top plot is the map from the Antelope product of Météo France. So it's a product based on radars corrected with Météo France rain gauges. So I think it's the best product that we can have for a specialized rain in France. And here is the map that we produced with our system, so we can get the right patterns and the good order of magnitudes of the rain accumulation. This is the same for 2 different days. So this is daily accumulation for 2 very strong events in the south of France. So sorry, it's not exactly the same colors. So here is the map that we produced from the SML that you show on the picture. And here is the Météo France radar accumulation. I think it's not the same product. It's not corrected with rain gauges. So it's a raw radar product. So again, we have the same patterns here with the maximum of rainfall above 100 millimeters in one day in this part of mountainous area near Montpellier and Nîmes. Also a bit of rain here on the coast near Nice, and this is for a second day a year before. So all the area is not covered because this sensor were not installed at that time. So again, it's quite in agreement. We can have the same patterns of rainfall here near Nîmes, and this line of strong rainfall to the south, to the coastline. But of course, these very good results also hide a few errors. So this is a very synthetic figure, so don't mind about the colors. It's almost the same data. But what is plotted here is a quantile curve. So each point is a quantile, here recorded by our sensors, SML sensors, and here it's the corresponding rainfall rate for the radar plus rain gauge product of Météo France along the same pixel, so along the same path on the ground. So it's at 5-minute resolution. It's for a very large number of SML, about 500. So it's all the SML that we have in the south of France for 20 very rainy days in the late 2022. So it corresponds to rain accumulation from 50 to 400 millimeters, these 20 rainy periods. And this is what we get. So of course, we don't have exactly the same patterns. And mainly we think that it's due to 3 different issues acting on 3 different ranges of rain intensities. I will precise that just after. So the first one here is not very visible, but it's important because most of rainfall intensities are low. So it could be interesting to have a zoom here, and it's due to detection issues. We work in the Caillou band, and in the Caillou band, the attenuation is not very strong for light rain events. Probably for 1 or 2 millimeters per hour in winter, when the path is not very long because the melting layer is low. It's just a few maybe 0.1, 0.2 dBs. So it's quite hard to detect these events, and the current neural network that we use to do this is not perfect, and we know that we miss few rain events when especially with stratiform rain in winter. So this is probably one explanation for the discrepancy that we can see here for very light rain. Then we have a second area here for intermediate rain intensities, where we tend to overestimate rainfall when compared to the radar rain gauge product. This is probably due to two phenomena that act in the same way: the wet antenna issue and the melting layer issue. So Filippo talked a lot about the melting layer issue, which is very important. So in this, of course, in this plot, we don't take into account the melting layer. We use a 2 layers model, ice and liquid rain, but we never take into account the wet antenna. So when there is a bit of rain standing on the antenna, that causes an over attenuation that we attribute to rainfall. So these effects are mostly important when the rain is light and when the melting layer is low, because they have a more important relative power. And the third part is here for the strong heavy rain events above 40 or 50 millimeters per hour. And we think that is due to atmospheric radiations. So I will talk about this just after. So this is another plot. It's the same at the beginning, but when we target another satellite, which emits a lot of signal, a strong signal over this channel. So here it's the upper part of the Ku band with horizontal polarization. But this satellite emits no signal for another part of the Ku band, the lower part of the Ku band. In this case, when it's raining, what we measure is not the attenuation of the signal coming from the satellite, because there is no signal coming from the satellite, but it's the increase of background noise, mainly due to the emissions produced by the raindrops themselves. So our sensor basically acts like a radiometer, and so we can measure an increase of the signal when we measure the decrease of the signal. So of course, when the signal, the red curve is 10 or 20 dBs above the background noise, we don't have to take into account of the background noise. But when it starts to be in the same order of magnitude, so when the rain is heavy and the signal is low, then the decrease of signal due to rain is compensated by the increase of signal due to atmospheric radiation. And we have to take into account this to do good rain estimations. So basically, with some hypothesis, we can have this formula. So if we measure the signal on two different channels, and if we have the baseline for each channel, we can have an estimation of the rain transmittance, and so from the rain transmittance of the rain attenuation by applying this formula. So we have to do a few hypotheses. We have to suppose that it's the same brightness temperatures for both channels. We are close in frequencies, so it's we have to have no satellite signal on channel 2, and we have this to suppose that we have the same gain on both channels. And if it's not the case, we will adjust one of the two curves to compensate the difference of gain between the two channels. So we applied this in France and in Ivory Coast. It's very interesting. So this is in France. So basically what is plotted here, so it's for an experiment that we did in France. We had 6 rain gauges together with 3 SML that are in these cases with no signal on one of their channels, and together with 4 SML, which are in the standard case where there is a strong signal for all channels. So we plot the quantiles of the measurements for the SML against the quantiles of the measurements for the rain gauges, and we get this curve. So this light curve is what we get when we don't correct the atmospheric radiation for this kind of SML. So it's critically low. Of course, we very strongly underestimate the rain rates, especially the strong rain rates. And this is in red what we get when we apply this correction. To be honest, when we apply this correction together with a standard melting layer correction, the one explained by Filippo just before. So it's very good, and we don't have any bias even for strong rainfall. And when we use another satellite which emits a strong signal for all channels but without correction, it's not that bad for low rainfall because the atmospheric radiation are negligible, but we start to underestimate very strong rainfall. So in France, we were really convinced to have a good correction of this phenomenon. We applied the same in Ivory Coast, where it's most critical because we don't have such green satellites. We just have satellites with a weak signal. So we add, so this is for 2 different satellites, the colors. And so in light, it's what we get without correction. And here it's what we get with the correction. So it's far better but we still underestimate rainfall. And we still don't understand right now why we underestimate rainfall in Ivory Coast. So it's especially clear if we plot a standard comparison of rain measurements. So in black, it's a rain gauge. And here for two polarizations, it's measurements that we do with a sensor which is very close to this rain gauge. So before correction here and after correction here, it's better, but we still miss like 15 to 30% of the rain, and it's quite systematic for all the experiments that we have done. So it's the same for another rain gauge. And just to conclude, a few slides about melting layer and wet antenna. So back to France, we plot exactly the same plot as before. So it's the quantiles for a very large number of SML against the radar rain gauge product. But we do this plot for different rate thickness. So it mainly the freezing level here, the parameter. And so we can see that for very high freezing level, we don't see this error for intermediate rainfall intensity. We see the saturation effect and the atmospheric radiation effect here. But if the freezing level is very low, it starts to be critical, we critically overestimate rainfall. So we think it's due to a mix of wet antenna and melting layer effects, because they are very, they exactly act in this way. They are all expected to exactly act in this way. So a few slides about a wet antenna. So we did an experiment. We covered our sensors in Toulouse. So it's in the Météo France campus in Toulouse. We have a few sensors here to make tests. We use standard relationship to parameterize the wet antenna effect. A0 is the maximum effect that we can have. So to get this value, we just put water on the antenna and we check what we get. So it's a bit less of 1 dB. It's very preliminary results. We don't pretend to have a very strong results here. And for A0, we use it in the literature, 10 millimeters. So it's a standard value. And we did an experiment by comparing what we measure. So it's also a quantile plot without covers against with no covers against the quantiles with cover. So in black, it's what we get with no correction. So of course, we have more attenuation with no covers on the sensors. And in orange is what we get with this very standard correction, raw correction. So it's not that bad. It's not adjusted, so it's not that bad. It's a bit too more corrected, if I can say. And in blue, it's just what we get when we adjust to the line. So it's normal that we fit the line because we wanted to fit the line. But now we will try to apply the blue correction to other data to check if this correction makes sense. And just this is the last slide. About the melting layer, we are just starting working on it. So we try this model, which is a standard model as well. We suppose that, there is a melting layer with a given length and a given extra attenuation power, this MX. So we tuned MX with rain gauges, also in Toulouse. And the idea is to apply it with other data to check if it makes sense. But it's a dangerous approach because other parameters could be tuned in the same time in this formula. And another approach that we will try in the next months is through an experiment. So near Paris, we have installed stations close to two vertically pointing radars in W and in X bands that are directly able to see the melting layer, its thickness, for instance, and we will try to calibrate this from a more physical approach. So thank you very much. And also don't hesitate to contact me or my colleagues for any questions or to share data. We are open to extend the data we use to do these experiments. Thank you very much.
Thank you, François, for this nice presentation with very motivating results. Is it any question from the audience to our speaker?
Yeah, Filippo.
Yeah, as you can imagine, I would like to discuss with you for not 1 day, for 1 month. Yeah. Because you are providing a lot of experience on the field, so this is very interesting for us because by iterating experience on the field, the models, it is an endless loop, but we can provide better service. What I would like to ask you is that it concerns the change of satellite power made by operators, but I am obsessed by the lack of cooperation of the operators. Even if in our teams we had a company that was a close partner to Eutelsat in many other projects, they were unable to find any help, any suggestion, any hint about maneuvers. So everything happened at the random sometimes,
Yep.
and it created some problems. The worst happened with that sudden change of power during a heavy rain. So
Yeah.
our algorithm was hung on the rain on the wet status for 2 months because the different changes, different power altered the reference levels, and the algorithm was locked. So I would like to ask you, how do you cope with those problems?
Yeah, so yes, it's a very, very good question. Indeed, there are these sudden changes. There are 2 points. So the algorithm that we use to classify rainfall sometimes can filter the sudden changes. So it's trained. So we have labelized manually a lot of data compared with radars or with any data we have around, and we have trained the algorithm, the LSTM, the machine learning algorithm, to identify the signature of rainfall. So when it's a very sudden and strong change, so for instance, if it's steady at minus 10 dBs and it suddenly drops to minus 20 and it doesn't move, the algorithm will filter automatically and will not identify this as rainfall. But it's not working all the time, of course. It doesn't work when it's small changes, like 2 or 3 dBs. So in this case, unfortunately, the algorithm can identify it as rainfall and put rainfall during a few minutes until it's steady again. And the second issue is when it happens during a rainfall event. So for instance, if there is a stratiform event lasting 5 or 6 hours, the typical attenuation we get is 0.5 dBs. And if there is a change during the event of 1 dBs, of course, the algorithm will not detect the change, and we will just consider that it's 1.5 instead of 0.5 dBs of attenuation. So it's an issue.
Okay, thanks.
It's the question from Martin now.
Yes, thank you for a nice presentation. I wanted to ask regarding possible differences in drop size distribution in Ivory Coast and France, if you thought about changing these parameters of parallel or something like that. Yeah.
Yes. We tried with different distribution in Ivory Coast. So we tried Marshall Palmer, of course, Chero, and also distribution. It's a Momoni article calibrated during rainfall. It changes the result, but first it's not better. Actually, it's a bit worse. Like instead of having 20% of underestimation, we have 25%, and in all cases, it doesn't explain the difference. It's not the good order of magnitude.
Thank you.
But probably the issue that we have in Ivory Coast is the sum of different phenomena. We think maybe a change in the rainfall intensity during the fall, plus a change in the droplet velocity, plus an effect of the DSD, plus something else.
So I would like to ask also if you already made some tests on integrating different opportunistic sensors with SMLs, or you are just focused on this one technique?
We just have done SML, but we want to merge with CML. It's hard to have data, so we are discussing with an operator in France, and we hope to have data in a few months. And so, of course, we will try to merge both kinds of data. And another merging that we are working on is with satellite information. So the idea is not to provide accurate train maps, but to be able to provide no casting, even in the case when, for instance, the rain comes from the sea. We don't have sensor in the sea, especially in Ivory Coast. So we try to merge satellite products with ground data, SML data, to provide at least qualitative no casting, like no rain, light rain, strong rain.
Very nice. Okay, so thank you very much.